right, so let's see if mic is on. Mute, unmute. I think it's on. Right, so I thought lightweight talk would be appropriate for this experimental project, which essentially I wrap up in a few days, and I will show you. So first of all, what is this? I mean, why do we care about this information? And most of the things you find in PDG are hadron resonances. And why there are so many of them? Since essentially it's easy to understand if you look to the way how constituent meson and baryons are formed. So they are made of two mesons. They could be the same or could be of different quarks, and then baryons made of 3 quarks. In the standard model, we have 5 quarks that form hadrons. The T top quark does not form. It actually hadronizes too quick. It decays too quick before it forms the hadrons. And then you get, from just putting, instead of the Q and Q prime here, different quarks, you get roughly 10 classes of mesons and 24 classes of baryons. So, and that gives you only ground state. Every class then can be excited, and it gives you an infinite layer of the hadronic resonances. And that's why the book has this thickness. I mean, you've seen this, right? Couple of words on the excitations. Essentially, if you look at the pion, this is the lowest state in the excitation layer. The rho meson would be the other one, and they both have a sort of 1s spherical wave function. The only difference between is the spin orientation. And then, as in nuclear physics, you can have further excitations, radial excitations where you change the size of the hadron, and the orbital excitations when you introduce the orbital angular momentum between quarks. And that's actually, we give the different names to different levels. So all of these are pions excited in different ways, but then we call the upper one is rho, and then there is a B1, A1 states that are higher. So it has been developed over a long history when we discovered first these hadrons, and that's why there is a lot of history in the naming, in the way how we encode that. There is a lot to now deal with. In PDG, since a few years, it's nicely organized in PDG Live. You click on the PDG Live button, you get all of the classes of hadrons, mesons, baryons, and every class you see the list of the observed resonances, and then clicking by every resonance, you get more or less full information summary of the state. There is internal note, and this is central to all encoding, is this PDGid. And this is different PDGid to what is in SVS tables exported earlier. So, and actually in PDG inside, there are 3 different IDs. They all call PDGids. And I will show you, there is more. So it's a history of more than 50 years. You see this collection of the book that started in 1957 from the journal review, and then there were paper cards that people filled on the properties of the particles. It was digitized in later last century, and since then we have a, thanks God, MySQL database, and it's better, but there are still, you know, a lot of history inside. So it's done nowadays by group of more than, I mean, roughly 200 people who have, you know, filling this database and then keeping track of all discoveries as their side projects. And there is a central particle data group that sort of manages this activity and puts latest improvements. There is a lot of work of many people, and the result is these nice books. You probably, so actually my first experience with this book was on the first day I moved to my dormitory because it was actually used everywhere to hold the door, to lift the monitors, and was super useful. And then later I realized that there is another application. No, jokes aside, it's actually a good document and has a lot important that we need to understand and appreciate. Now, internally, when you encode, what you need is actually our job in PDG is split 2 phases where we encode the information based on the journal publications, and then we check each other. There is overseeing phase. And then every encoder gets roughly 10 papers per year, per person per year. That's not much, but still it's some work, and it requires a lot of attention since it's a graphical interfaces, and then there are error-prone. There is easy to introduce the mistakes, and they happen and actually get propagated. That's how we come to these databases that has been released, and finally we have an opportunity to kind of computationally review the content and then see and actually fix problems. So this year in June, Particle Data Group announced a release of the large chunk of the internal information. So actually this database became accessible. So there've been a lot of discussion. What should we do? We should print these big books, or we should stick to the machine to the only web page, or should we? One of the push from the community was to make this programmatically accessible. That led to the publication of the databases, but also Python API, written by Jörg and the collaborators, who is a group leader of PDG. And then the REST API has been existing for some time. This is a JSON file that you can download directly from the page. So there is a lot of information in addition to these SV files that are now available. This is in addition to particle masses and widths, you get branchings and the decay. You get decay fractions and list of the decays. And right, so the database has a non-trivial structure. So there are 5 databases that contain different information. So the easiest one is the info, just tells you what is the release day, and then all meta information. And then the one that you would look first. Well, and here's a snippet of the Julia code that loads this database. So essentially, it turned out to be very easy to load a MySQL database and turn it into data frame, and then you have everything. You can wrangle this database easily. So, and ChatGPT knows extremely well how to deal with this stuff. So, all right. So quickly realize that there is a lot of information stored in the PDG info and PDG data, as well as the PDG particle. These are 3 main databases. And the algorithm to find the information that you need is to start, since what we think in terms of is the particle names. So you start with the name of the particle. From this, you understand what is the PDG ID. This is the main key that is shared between tables. And then from PDG ID, you get particle data that has the masses and widths. And then from particle data, you can request all of the, that's funny, this particle data has the numbers, but it doesn't tell you what it is. So the description is stored in a separate table. So we have to left join these 2 tables and to access the descriptor, essentially. But this is straightforward operations on these databases, and this is done. That's actually what is done in the package. You can also access the separate data frames that are pulled from the MySQL. And actually, my main motivation was to understand the structure and see inconsistencies and find this PDG ID that I need for my encoding. So quickly on issues, and actually the physics-driven issues. So we have isospin symmetry, meaning that due to the fact that light quarks are light and have identical masses, several hadrons, several families have the same properties. We don't need properties of the, let's say, K star plus, K star minus. So particle and the particle obviously have the same properties, but then K star 0 would have very similar properties as K star plus. That's why we are in PDG, they encode it as a 1 node. So that has this generic particle has a collection of information that is common for both resonances. And it's the same for many charge, for many particles that are sharing the same multiplet. So essentially this UD, UU bar, DD bar, and DU bar, they will be all excited states for these configurations will all have the same properties. In PDG, it's a generic node, but you can, for some of them, also charge-specific node exists, and that makes things rather complex, since for some of them there is only generic node, for some of them there is a charge specific, there is no generic, and there are something, I mean, when you look at the database, something to deal with. And when we export, when we want to produce, I think we used to think in the charge specific states, but then one has to understand that some properties that you're going to access comes from this, from other state and multiplet measured. And that's something to be still to be think about when we want to produce a clean database, how we deal with these cases. And then current API starts with this method PDG that where give you a guess name. So I've seen it in one of the probably particle package in Python has this guessing, which I found very nice when you don't know how particle is called exactly. So you can just guess. So here I say D1, that's what I want. And then it says no exact key, but then the first actually suggestion that it gives me is the correct one. So that's what I want. Maybe I add the charge later. So and then you can correct and have exact matching the key, but you can also deal with your first guess. And then you can call for properties. It will give you mass and width together in the one data frame. And if you can actually follow up then saying mass and width, and then you can also access decays and see it in the form of the data frame. It's not nicely printed as Johannes showed us, but this is a full information in the full glory that you can deal with. Right, quick summary that PDG will keep releasing the data more and more, and we get to deal with the format that's there. MySQL is internal format, new releases will be in the same format. It gives us actually possibility to make our digital access more sophisticated, but we have to deal with historic records. It's not clean, not consistent, and it's on us to improve that. And I believe, in my view, is that clearly we can use this as the tools to clean up and write the export the consistent SVE or the table data to be accessed by scikit-hap, particle, or corpuscles. All right, that's it.
Thank you, Misha.